How the arch got its shape. In the beginning was the equation. It was born over 3 centuries ago, when mathematicians said that it described a beautiful curve, the surprising child of distinguished parents, the curve of exponential growth, and its companion curve of exponential decay, by taking equal parts of one and the other. Mathematicians called the curve described by their equation a catenary, because, they said, it was the shape of a hanging chain or a string of beads. And scientists said, if you take that catenary and flip it over, it will make a perfect arch. And along came an architect who said, I have a vision of a magnificent arch that will be light and slender at the top and will be sturdy and strong at its base, and will last as long as the arches built 2,000 years ago in Rome and still standing today, and maybe as long as the Great Pyramids built 3,000 years before that. And the engineer said, yes, we can do that. I will tweak your equation and flatten your catenary, and I will tell you exactly how much to slim it down from bottom to top. And you architects and engineers took the mathematicians' equations and made drawings and great columns of numbers, and took them to the steel makers and the construction crews, and the dream became a reality.
Here I have a piece of rope. If I hold it between my hands, it forms a curve. This is called a catenary curve, and it is not a parabola. It is its own type of curve with its own type of mathematical description. The word catenary is derived from the Latin for chain because it's the shape formed from any chain or rope hanging freely under its own weight. And you'll see this simple and beautiful piece of mathematics everywhere, from the wires in an overhead power line to the strands of a spider's web. But why do we see this curve appearing again and again in the natural world? To answer that question, we're going to turn to the world of bubbles. To minimise their surface tension, bubbles form perfect spheres. If we try to form a bubble between 2 rings, it cannot make a sphere, so instead makes a curved shape. This time, to minimise its surface tension, it makes the catenary. So a chain, like in the world of bubbles, wants to minimise its tension, so forms the catenary, and it is not a parabola. The parabola is the arc of a ball flying through the air. Its mathematical description is y equals ax squared plus bx plus c. By eye alone, it looks like a catenary. Galileo realised that the curve of a free hanging chain was very similar to a parabola, but something was amiss. The mathematical description of a catenary is actually quite different. It is y equals a cosh x over a. That's equal to a over 2 outside of e to the power x over a plus e to the power minus x over a. The curve changes as the distance between the 2 ends and the length of the chain changes, but they can be described with the same formula and are never parabolas. Man uses this natural form in the worlds of engineering and architecture. For example, the wires of a suspension bridge are parabolic due to the weight of the bridge it carries. But without this weight, it is more like a simple rope bridge carrying the same weight along its length and will again be a catenary curve. But if the catenary is the shape of a rope or a chain that minimises forces in tension, then by turning this upside down, we form an arch, which minimises the forces in compression. And it's actually the strongest kind of arch, strong enough to support its own weight. For example, that's what the master builders of the Middle Ages did to construct this, the ceiling of King's College Chapel in Cambridge. So to make the strongest kind of arch, you can simply mark out the shape of a free hanging chain and turn that shape upside down. So now that you know what a catenary curve is, you'll be able to spot it everywhere. So next time you see an archway, a bridge, or a spider's web, remember, you're seeing mathematics.
Hi, I'm Doug Patt, and this is How to Architect. The Fibonacci sequence, the golden rectangle, and architecture. In 1202, Leonardo Fibonacci was famously investigating rabbit reproduction and made note of a sequence that is now known as his namesake, the Fibonacci sequence. The sequence is a series of numbers derived by adding each number to the previous. That is, 1 plus 1 equals 2, 1 plus 2 equals 3, 2 plus 3 equals 5, etc. Plant leaves as they spiral around a stem, called phyllotaxis, in some cases follow a mathematical rhythm of 1.618. That's the same spiraling numerical rhythm seen on the skin of a pineapple, as well as the seed head arrangement of the sunflower and the base of a pine cone. In geometric terms, if a rectangle is drawn with one side equal to 1 and its perpendicular represented as 1.618, a desirable shape emerges. In 1876, Gustav Fechner did a study that determined people visually preferred the shape to other rectangles. It's thought that the ratio may have been used as early as the Egyptians in the creation of the Great Pyramids. Based on measurements of the pyramid at Giza, the hypotenuse almost precisely matches the number phi, or 1.618. It's also thought that Andrea Palladio employed the golden ratio of proportions. This is his Villa Rotonda, outside of Vicenza in northern Italy. Even the modern architect Le Corbusier used the proportions in his modular man study and, most likely, in the design of his Unité de Habitation in Marseille, France.
Most insane animal architects. Number 13. Sociable weaver nests. This bizarre bird is known for its unique nest. They gain their names because a large group of these birds will band together to build their nests. They're the largest bird's nests in the world, and they house hundreds of birds at a time. They also look super freaky. You'll only find these birds' nests in southern Africa, so there won't be any Hitchcockian attacks from the sky anytime soon from these birds. Number 12. Caddis fly. These are less nests and more exoskeleton. The caddis fly is a moth-like insect that has aquatic larvae that can be found in freshwater sources like streams, rivers, lakes, ponds, and springs. The larvae of this order build themselves an exoskeleton made out of anything they can find in their little ecosystem. This mainly means that they build armor out of shells and pebbles. This type of ingenuity is amazing, especially for an organism like this. To meld the various parts together, the caddisfly uses their own silk to connect them and form them over their bodies. They don't only build these cases either. Other caddisflies build nests to hide in. Number 11. Swallows. Swallows are pretty adaptive for not being able to survive in captivity. They can make their nests pretty much anywhere, no matter the altitude or conditions. They also pretty commonly build their nests in people's homes or barns. They build their nests out of whatever material is available, and some species even build nests out of their own saliva, which is used in the traditional Chinese bird's nest soup. They can also reuse other birds' nests in one of the examples of natural squatting. Number 10. Australian weaver ants. These ant architects are known for their unique nest building techniques. Thousands of these ants will band together to build nests made out of leaves. They use their own silk to act as a glue to keep these nests together. There's never just a lone nest either. You can see sometimes hundreds of nests grouped together because this species of ant stick to massive colonies. There are up to 1 million workers in a single colony. These aren't ants that you would want to mess with either. They are incredibly territorial, and they will not only bite, but they also spray acid into the wound so that it hurts even more. The ants excel so much at teamwork in building a nest that a large nest reaching a little over 1 foot only takes about 24 hours. Number 9, Bayeux weaver. This bird has one of the most self-explanatory names on this list. They're birds that construct hanging weaved nests. They are endemic to the Indian subcontinent and Southeast Asia. The lofty location of the nests makes them a harder target for predators as well. They're often built in or near sources of water. They are common in their habitat, but they move around a lot for a lot of various reasons. This bird also has 3 different subspecies, and they are the subject of a folktale in Indian mythology. Number 8, beavers. Beavers are pretty famous for their habit of building massive dams to protect against predators and make food easy to get. Beavers have got dam building down to a science. They can build dams fast, and they do all of their building at night to avoid most predators while they do it. They build primary dams and secondary dams, and they will defend their primary dams vigorously, but they typically don't do that for their secondary dams. Dams technically aren't the places that beavers live in. Their houses are called lodges. The dam is often built beside the lodge so that they can manipulate their surroundings and food levels. The lodges are built much in the same way, using twigs and branches, but the lodge has a well-protected underwater entrance. Number 7, bowerbird. These birds are well known for their nest-based mating habits. These love-struck birds spend hours to days building these color-coordinated nests. They've even been observed creating optical illusions to entice their prospective mates. Items that they gather are meticulously arranged to be pleasing to the eye, and their mating habits are so complex that humans can ascertain the pattern in the arrangement of the items. They do have a long time to plan their nests, though. They don't reach sexual maturity for 7 years, so that's a lot of time to plan the perfect nest. The bower's nests aren't even used. They're purely for decoration. Nobody ends up living in them. Number 6, prairie dogs. There are plenty of burrowing rodents that live in the world, but the prairie dog is probably the most familiar to a lot of people. They're native to the grasslands of North America, and they can burrow up to almost 10 feet into the ground. They do this because it's an important defense mechanism against the sometimes difficult environment. The burrows defend against intense heat, blizzards, floods, droughts, and bushfires. They even build little aqueducts to help gather rainwater for whenever they're short of it. They also build rooms that serve specific purposes. There are chambers for them to nurse their young, chambers for the winter, and chambers for the night. These smart little animals also build burrows that are specifically meant to prevent flooding from reaching into the main burrows. For predators, they build holes to not only hide from them, but also to listen to them approaching. Let's just say that city planners in urban areas should study prairie dogs more often. Number 5, red oven bird. This oven bird, or Rufus hornero, can be found in South America, and it's actually the national bird of Argentina. These birds build sturdy nests out of mud. They're named oven birds because their nests resemble a clay oven on top of a tree. These nests take quite a while to build too. They can take 5 days or even months to build. The nests are occupied by the birds for up to a year, long enough to mate, lay eggs, and raise their young. It is common to see several nests next to each other so that the birds can house all of their young. They also sometimes repair unused nests to use instead of building a new one. Their nests also can become the home of other species of birds once they are abandoned. Number 4, colored wasps' nests. This wasp nest gained its technicolor quality when biological science student Mattia Manchetti fed multicolored paper to paper wasps for them to build their nests. The paper wasps typically build their nests by chewing up wood until it becomes pulpy enough for them to form it into a nest shape. The wasp's saliva actually naturally waterproofs the nest as well. Number 3, Montezuma oropendula. That name may be a handful, and these nests might look like bats that were cursed to become straw, but they are birds' nests, we promise. These birds are endemic to the New World, or the Earth's western hemisphere. It also prefers tropical regions like South America, the Caribbean, and Mexico. The nests are made out of grass and vines, and they can be built high up in the trees. The birds are also said to have an unforgettable song, which is a nice way of saying stupid. It's been described as a bunch of bubbling sounds that turn into loud gurgling. The nests can be built for a colony of up to 30 individual birds. The colony of these birds is typically made up of an alpha male and then a large group of females. Number 2, honeybees. These important little insects are actually just one species of over 20,000 types of bees. Their nests are pretty iconic because they store honey, which is hugely popular all over the world. Their nests are built yearly and they contain a whole colony of bees. There are some subspecies of honeybees, including one that can't sting you, but the honeybees that we know and love is the western honeybee. They are the ones that can be used to farm for honey. Their nests are actually made out of wax, which is secreted from a series of glands that can be found in the bee's abdomen. These bees are disappearing though. Just recently, 7 species of bees were put on the endangered list.
And now for number 1. But first, be sure to subscribe for new videos every day.
Termites. All termites build some pretty impressive nests, but most impressive in sheer size is the cathedral termite. They build the largest mounds out of all the termite species. Their mounds can reach heights of 15 feet. They're considered to be the most complex structure in the insect world. They have a system of chimneys, pinnacles, and ridges. They even build a spacious chamber for the king and queen. They have a similar caste system to bees and ants, where workers and soldiers do all the heavy lifting for the colony. These unique little pests can be found on every continent except for Antarctica, but if you are looking for some, Australia would be your best bet.